Hello, welcome to Astronautics for Exploit. This is Dr. Ayenshola Ogundele. Mars In-Situ Resource Utilization, Space-Centric Approach for Successful Human Mars Exploration and Inhabitation. The focus points of my presentation are as follows. Benefits of Mars In-Situ Resource Utilization and Mars In-Situ Resource Utilization proposals. Over many years, Mars has been explored via robotics mission for better understanding of its features and composition of its abundant natural resources and possibility of existence of life. Presently, government space agencies, private space companies, and investors are planning human exploration of the red planet and eventual possibility of living and working on Mars for the betterment of humanity. Based on the envisaged longer human journey to the Mars and expensive resupply missions, attention is shifting towards Mars in-situ resource utilization, in which astronauts will make use of the naturally abundant local Mars resources to provide useful infrastructure and commodities and become independent of Earth resources. This will help humans to have viable and sustainable space exploration. Through Mars In-Situ resource utilization technologies that are presently being developed, future Mars mission astronauts will be able to collect space-based resources critical for their survival and transform them into breathable air, water for drinking, hygiene and plant growth, rocket propellants, building materials, and more. Mission capabilities and net value will multiply when useful products can be created from extraterrestrial resources. Through various research endeavors, several Mars in-situ resource utilization proposals have been put forward by the researchers, and some of them are harvesting of Mars carbon dioxide via refrigeration so as to fix it, electrolysis of water, and methanation of carbon dioxide to produce oxygen and methane. Use of water in the soil of Mars to provide hydrogen and additional oxygen. And the use of Mars atmosphere, which mostly contains carbon dioxide, to provide carbon and oxygen and a host of others. Benefits of Mars in-situ resource utilization. The various objectives behind persistent increase in investing in Mars in-situ resource utilization are to perform initial research and development of ISRU and characterize resources of Mars, especially water, in preparation for human exploration. To develop and evolve Mars ISRU capabilities to reduce the cost, mass and risk of human Mars exploration and enable new missions. To enable human exploration beyond Mars. Artist's depiction of humans living on Mars is shown in this picture. The various benefits of Mars in-situ resource utilization are mass reduction, cost reduction, mission enhancement, capability enablement, reduction in mission risk, and mission flexibility. Mass reduction. In-situ production of Mars mission critical consumables, such as propellants, life support consumables, and fuel cell reactants, significantly reduces delivered mass to Mars service. In-situ production of shielding materials for habitat, radiation, micrometeoroid, and exhaust plume debris, and surveyed nuclear power made from in-situ materials and resources will significantly reduce delivered mass to surface. Mars exploration portrait is shown in this picture. Launch cost. Reduction of delivered mass will lead to reduction in launch cost through smaller launch vehicles or reduced number of launches per mission. Reuse of elements by resupplying consumables may lead to reduction in architecture costs. Similarly, use of modular common hardware in propulsion, life support, and mobile fuel cell power systems leads to reduction in cost and reduced life cycle costs by reducing logistics. Mars Exploration Rover is shown in this picture. Mars In-Situ resource utilization will enable reduction in architecture costs through access to multiple service sites from a single landing site, thereby eliminating the need for multiple launchers. Also, Mars In-Situ resource utilization will enable direct Earth return, eliminating need for rendezvous and development of Earth return vehicles. NASA's Mars helicopter is shown in this picture. Through Mars ISRU, there will be increase in robotic and human service aspects of Mars and its environment, and this will lead to the boosting of various Mars missions and technology enhancement. Similarly, increase in delivered and return payload mass to the Mars will occur because of Mars In-Situ resource utilization capabilities. Artist's concept of a proposed Mars sample return mission is shown in this picture. Mission flexibility is another benefit of Mars ISRU. Reduction in mission and crew risk due to increased shielding will lead to mission flexibility. Increased mission flexibility due to use of common modular hardware and consumables is also of utmost importance. Mars exploration is shown in this picture. Reduction in mission risk. Due to the reduction in Earth launches and sequential mission events, there will be a reduction in mission risk. Also, mission risk reduction will occur due to Mars service manufacturing and repair. Artist's concept of a proposed Mars sample return mission is shown in this picture. Capability enhancement is another benefit of Mars ISRU. ISRU capabilities will reduce architectural life cycle costs through the Mars ISRU. Commercial sector capability will be enhanced. Also, the following capabilities will be enhanced: low-cost mass-efficient manufacturing, repair and habilitation and power infrastructure growth, energy-rich and extended missions. Illustration of 2001 Mars Odyssey is shown in this picture. Mars ISRU proposals. The various proposals for Mars ISRU are Mars atmospheric gas capture and processing, cryogenic liquefaction and storage, Mars water mining and extraction from regolith, Mars water cleanup, Mars oxygen and propellant reduction, and Mars electrolyzer. Mars atmospheric gas capture and processing. Several technologies have been proposed for the capturing and pressurizing carbon dioxide from the Martian atmosphere, which is required to purify it from the minor components and to pressurize it sufficiently in order to obtain a significant feed rate. Freezing at cryogenic temperatures, mechanical compression and absorption pumping are the proposed technologies. Artist's impression of the Theon-1 mission to study red planets is shown in this picture. Mars water mining and extraction from regolith. Water condensation is a cooling process to convert Mars water vapor into liquid water that has a very low vapor pressure, just above 0 degrees Celsius. Previous testing in this process has not identified any issues. Nuclear thermal propulsion ideology is shown in this picture. Mars water cleanup. NASA's Phoenix lander mission to the northern hemisphere of Mars found significant amounts of water-soluble constituents in the Martian soil. These constituents represent potential contaminants to water produced from soil processing. Mars technologies are being developed for Mars water cleanup. The Martian system is shown in this picture. Mars electrolyzer is another proposal. Water electrolysis will be a critical step required to support Mars ISRU. Water electrolysis is a common need for multiple surface systems, and ISRU projects will continue collaboration in technology development. Currently, available water electrolyzers are already highly efficient, although analyzers that are not as sensitive to impurities will need development and improvement. Illustration of astronauts on the Mars is shown in this picture. Mars surveys cryogenic liquefaction and storage, various laboratory testbeds and oxygen liquefaction and storage under Mars environment simulation are being carried out. Cryogenic fluid storage systems are flown in Mars missions, but for limited durations and not with integrated liquefaction systems. An illustration of a Mars ascent vehicle is shown in this picture. Mars oxygen propellant production. Mars oxygen and fuel production has enjoyed a greater amount of attention over several years. The development focus has primarily been on atmospheric processing technologies. Several prototype systems of Mars oxygen are being constructed. Example is the Mars Oxygen In-Situ Resource Utilization MOSI. Earth Return Bureau is shown in this picture. MOSI is an example of a solid oxide electrolyzer cell, which is a fuel cell that runs in rivers and uses carbon dioxide to make the gases carbon monoxide and oxygen. In a fuel cell, fuel and oxygen react to make energy and a stable chemical product. The most common example is the hydrogen fuel cell used in some automobiles, which combines hydrogen and oxygen to make water and electricity. A fleet of craft on Mars is shown in this picture. Mars oxygen propellant production. MOSI was designed to make at least 6 grams of oxygen per hour, and its main job is to show that we can rely on this technology to keep future crews of astronauts alive and return them home safely. The MOSI instrument is shown in this picture. For more information, contact Astronautics for Exploit. You've been watching and listening to Mars In-Situ Resource Utilization, Space-Centric Approach for Successful Human Mars Exploration and Inhabitation, presented by Dr. Anyashola Ogundele, with the focus points: benefits of Mars In-Situ Resource Utilization and Mars In-Situ Resource Utilization proposals. Thank you.